All right, welcome ladies and gentlemen to section 2.3, or at least the first half of section 2.3. Today we're going to be beginning our study of analyzing functions, or analyzing graphs in particularly. And there's quite a few things that go along with this. The first is the idea of a zero of a function. Now you may have heard of zeros before, you should have by now through your study of Algebra 2. A zero of a function is any x value that makes the statement f of x equal to 0. So let's take a look at an example. If I was to just start with a simple linear example, let's call it 2x plus 7 is equal to f of x. Call that my function, 2x plus 7. I want to find the zeros of my function. That means I'm going to set 2x plus 7 equal to 0. And I'm going to solve for x. So I get 2x is equal to negative 7, and then I get x is equal to negative 7 over 2, which is the same as negative 3.5. So that tells me the zero of this linear function is negative 3.5, basically saying if I was to graph this function, if I go 1, 2, 3, 4, at negative 3.5, is where this function is going to cross the x-axis. That's my x-intercept. This is also called x-intercepts, by the way. The zero of a function is your x-intercept. And graphically, we could go like this. We could come up here to 7 and find the y-intercept, and we could graph that line like that, if that was the question being asked. But let's try a different one, because linear functions are not quite that interesting. So let's try if I gave us the function f of x is equal to x squared plus 6x plus 8. And I want to say, where are the zeros of my function? Well, in order for this to have the zeros of the function, I got to set it equal to 0. And this is a quadratic equation, so I want to see first if it will factor. And remember, if it doesn't factor, you have to use the quadratic formula. And in this particular case, it will. This is x plus 4 and x plus 2. And in order for this to be 0, you probably know this already, x plus 4 has to be 0, and x plus 2 has to be 0, which means the zeros of my function are negative 4 and negative 2. And again, graphically, this looks like this. It means at negative 2 and at negative 4, I have x-intercepts on my function f of x. And it's a quadratic, so it would look something along that line. But the graph is not the important piece here. Finding the zeros of my function r. And we could go farther. We could go to cubic functions. We could go to quartic functions. We could go to something like this. Let's call f of x equal to, let's go x to the third plus x squared minus 4x minus 4. I think that will get the right thing. In this particular case, I'm going to say, okay, well, what are my zeros? I need this to be 0, and I'm going to go ahead and factor. But since it's a cubic, it's got 4 terms, I can try to factor by grouping first. And the first 2 terms, they have a common factor of x squared. So I'm going to take that out, and I get x plus 1. And both of these terms have a 4 in common, or a negative 4 in common, so I'm going to factor that out. I'm going to get an x plus 1 here. They both have an x plus 1, and then I get x squared minus 4 times the x plus 1. And you might remember this from previous lessons. And I'm going to continue factoring this, and really the whole idea is to find all of the zeros of the function if we can. So x squared minus 4 continues to factor down to x plus 2, x minus 2. And we have that x plus 1. And the zeros of this function are all of the things that make these factors 0. So I get x equals negative 2, I get positive 2, and I get negative 1. So those are the zeros of the function. Just refreshing our memory here for finding what x value makes the function 0. Or in other words, the x-intercepts of the graph. So let's look at increasing and decreasing parts of a function. So there should be a slash right there. This is increasing or decreasing parts of a function. And what this is it's an interval for x where the y value is increasing, decreasing, or constant. And I'm going to give us a basic example of a graph. And let's say I have this graph right here, and at x equals -1, the vertex is 4. And what we need to do is we need to look at this function reading the graph from left to right. Reading from the graph from left to right. So we need to figure out where is this function increasing and where is this function decreasing. Or in other words, where is the function going up and where is the function going down? Well, in this particular graph, as we read from left to right, this piece of the graph is increasing. The y values are going up. Well, right out here, it goes to -infinity. So this means it's increasing from -infinity up until the x-coordinate of that vertex. And the x-coordinate is -1. So it's increasing from -infinity up until -1. And then as soon as it passes -1, it starts to go back down because that's the vertex. And so it's decreasing starting at -1 and going all the way to positive infinity. It always will decrease on this side. Let's see how this can change a little bit here. So let's say we have this particular function, some cubic that looks like this. And if you look at the cubic without giving it any numbers just yet, as we go from left to right, it starts off by increasing. And it's increasing right to that point. So that point is very important to us. Then from this point, it starts to decrease. And it continues to decrease right to that point right there. We're going to later call that a minimum. The other one we're going to call a maximum. And from there, it begins to increase once again. So let's give these some numbers. Let's give that a number of -1, and let's give that a number of +3. It doesn't really matter what those numbers are right now. You'll find out those numbers from your assignments. So on the increasing interval and the decreasing interval. So we found that it was increasing starting way over at the left of -infinity, and it stops increasing at -1. Then from -1 all the way up until 3, it's decreasing. And then from 3 all the way to infinity, it's increasing. And there you have your increasing and decreasing sections for the graph. Now you got to remember, this is always the confusing part for people, is the intervals for x. Notice we're talking about the x values here. I don't care what the y values are in these cases. All I'm doing is I'm looking to see where is this function increasing, where is it going up. Then I look to see where is it going down. And then I continue to see where it's going up in this particular case. Now we could do all sorts of different graphs like this. We could look at a graph that does this, like an example of a quartic function. This is something like an x to the 4th power would look like. And we can see that whatever this value is, on this side, it's decreasing. Between this value and this value, so we could say it's decreasing here. It's increasing here from this point to this point. and then it's decreasing from this point to this point, and then it's increasing again to the end. And I don't really care what these values are. If I called this A, B, and C, we could look at this as increasing and decreasing sections. It's beginning by decreasing, so this particular function is decreasing from negative infinity all the way up until A. Then, from A to B, it's increasing. And from B to C, it's decreasing. And then from C to infinity, it's increasing. Now, it might be nice to know how to find A, B, and C given some ugly function, but we're going to talk about that in class when I'm going to teach you guys how to use your calculator to solve for some of these things here. Which then, if you realize these points are very handy, it's very handy to know what those points are. We're going to call those points relative minimums and relative maximums. And the straight definition of this is it's a point on the graph that is higher or lower than all points near that point. And I'm going to teach you guys, like I said, how to find these things on your calculator. But if I gave you that quartic function again, or some other function that looks kind of like it, if we called this the point -3 and this -2, if we called this the point up here, let's call that 1, and let's call this 5, and we'll call this -5. So we look at little parts of the graph, and if we looked at just this section right here, there is a minimum on this section of the graph, and that minimum would occur right here at -3, -2. So we would say this function has a minimum at the coordinate -3, -2. Then we look over here, and at this section, it has a maximum, or a relative maximum, at the point 0, 1. And then likewise, we would go down here. We notice here on this section of the graph, there is a minimum again. And we're going to call that minimum 5, -5. So in these particular cases, this one here is a relative min. This one could also be called a relative min, but we also call it, because it's the lowest point on the entire graph, it's also called the absolute minimum. And this point here is not the highest point of the entire graph, so we call it a relative. So if it's not the highest point on the entire graph, it's just called relative. If it's not the lowest point on the graph, it's just called relative. And if it's the lowest point on the graph or the highest point, we call it an absolute. So you notice here at the point 0, 1, these points here always continue to go up, which means there is no absolute maximum on this particular function. All right, I think that's good for relative min and max. Let's move on to piecewise functions. Piecewise functions are handy because they actually model real-life situations a little more than you probably think. So we're going to start with the function f of x is equal to, we're going to call 2x plus 1 when x is, let's start with 0. Let's go x is less than or equal to 0. And we're going to call the next function, the other part of this function, negative x squared when x is greater than 0. So what we need to do is we need to set up a set of axes. And since 0 is the place that things are going to change, I need to think about what's happening on the left side of 0 and what's going to happen on the right-hand side of 0. So this is the left side. This deals with all values of x that are less than 0, and that's everything on the left side of the y-axis. So here's what I need to do. I need to figure out what is happening at x equals 0. Well, at x equals 0, that occurs on this function. So I would start with the y-intercept of 1 with a slope of 2, but I can't go to the right because the function 2x plus 1 does not exist on the right because that's not less than 0. So I need to go to less than 0. So I need to go in the opposite direction. I need to go down 2, left 1, and I need to go down 2, left 1 again. And I don't get to just draw a big straight line because I can't draw a line on the right side of 0. So I'm just going to draw this direction. And there's the first half of my graph. The next half of my graph occurs on the right-hand side of 0, and it's going to follow the function negative x squared. Now you might recall that the function negative x squared looks like this, goes through the origin, and goes like this. Now, the problem is this is only for x is bigger than 0, which means I can't use this point, and I need to make that an open dot. So at x equals 0, normally this function would be at 0. So since x does not equal 0 for this one, I have to create an open dot. Then I can only go to the right. So on a quadratic function, if I plug in 1, I go 1 down. If I plug in 2, I go 4 down. So here's this, and now I get my nice quadratic. This is the graph of f of x. Now, if you recall the question from the quiz, something along the lines of this, if I told you to do f of 2 minus f of negative 1, f of 2 exists when x, that's 2 is bigger than 0, so I'm going to plug it into this function. So it's going to be negative 2 squared minus negative 1 exists in this function minus 2 times negative 1 plus 1. And I'd get negative 4 minus, that's negative 2 plus 1 is negative 1, so it's plus 1 equals negative 3. Okay, so that's just kind of like that quiz problem that we did the other day. But this is really what I want to get at, is graphing the function. Let's try a slightly different one here. Let's look at the function f of x is equal to, let's break this into 3 functions this time. Let's go with negative x minus 2 for x is less than negative 1. Let's call the next function 3, where when x is between negative 1 and 2. And my next function will be, let's go with let's go with negative x plus 3 for when x is bigger than 2. So you notice here, this set of numbers here is my domain. My domain exists for all real numbers. It's all the numbers less than negative 1, it's all the numbers between negative 1 and 2, and it's all the numbers bigger than 2. So here's what we need to do. we need to set up our axes again. And sometimes what I do when I graph these type of functions is I go, well, what is happening at certain values? So there's things happening at, ooh, that's yellow, doesn't work. There's things happening at -1 and at +2. So at -1 right here, I kind of just do a dashed line. Even though it technically doesn't exist, I like to just put it just in case. And then over here at +2, there's also something going on. I basically broke this graph up into 3 separate pieces. Stuff on the left of -1, stuff between -1 and 2, and stuff on the right-hand side of +2. So again, here's what we need to do. We need to look at just piece by piece. So let's look at what would happen at -1. At -1, if I plugged in -1, I would get -1, which is +1, -2. So here's what I'm doing. I'm saying f of, well, I can't do that. That doesn't make sense. I'm plugging in -1 to this function. But I know it doesn't exist there, so I'm going to use an open dot. But -1 makes +1. -2 is -1. So I would know down here, at the -1, it would look like the function is at -1. So I'm going to use the open dot. And then, because it's a negative x value, it's a negative slope, which means I can't go to the right, because that doesn't exist to the right of -1. So I'm going to go up 1, left 1, and up 1, left 1 again. And that's going to create the left side of my piecewise function. So I've taken care of that piece. Now I need to look what happens between -1 and 2. Well, between -1 and 2, it's the function 3. Well, 3 is a horizontal line where all of the y values are 3. And since it's included for -1, I get to use a closed dot. And I get to use a closed dot at 2. So it's a line with slope 0. It's a horizontal line here. And there we go. We've now taken care of the middle piece. And then I need to look to see what happens at x equals 2. If I was to plug in x equals 2, even though I can't, I'm going to get an open dot right there. I would get -2 plus 3, which is +1. So I get to use an open dot right there at +1. And then I'm going to use the negative slope to go only to the right. I'm going to go down 1 and right 1. And I'm going to go down 1 and right 1 again. And I'm going to get my negative slope going in this direction. And there we have now graphed this piecewise function f of x. All right, this takes lots of practice, but it's a very doable skill, just thinking about each different piece of the function and where it's defined. Notice I couldn't really cross these dotted lines with each individual function because they don't exist in each other's space. All right, so the last piece here is the idea of an even or odd function. Now you need to understand what these two statements mean. It's an even function if you plug in a negative x and get out the original function. Whereas it's an odd function if you plug in a negative x and get out the opposite of the original function. So let's take a look at something like that. What would be, and by the way, it's either even, odd, or neither. It's one of these three. A function could be even, a function could be odd, or it could be none of those two, which is most likely the case for many of our functions that we're going to be dealing with. But every once in a while we get a very special case. Even is symmetry across the y-axis. So a quadratic whose vertex is on the y-axis, that's really kind of ugly, but this is an even function because the left side, this side, is exactly like the right side. So there is a symmetry that you can fold on the line y equals, or on the y-axis. Whereas an odd function would be a cubic function. There's more than just cubic functions, by the way. Would be a cubic function that looks like this, where I can rotate this graph 180 degrees around. I could flip this over, and I would get this the same exact looking graph. And you'll notice that this upward point would go downward here. This upward bump would go down there bump. You can rotate your phone, rotate your computer, whatever you're watching this on, you can rotate it and notice that the rotation around the origin, so this is symmetry about the origin. It's a rotational symmetry. So let's take a look at what we would do to solve and figure out whether or not a function is even, odd, or not, neither. So I'm going to say we have the function x squared plus 2. So in order to determine if it's even or odd, algebraically, we need to do f of the opposite of x. So I'm going to plug in negative x, I'm going to square it, and I'm going to add 2. Well, if I square a negative x, I get positive, right? If I square a negative, I get positive. So I get x squared plus 2. And then I look at that and I go, hey, this x squared plus 2 is exactly what I started with, and therefore, that's my original function f of x. So that means that f of negative x is equal to f of x, and therefore, even. And likewise, I could say something like this. If I told you f of x was in fact the function x cubed plus x, and I plugged in the negative x, and I got something like this. I would say, okay, negative x cubed plus negative x is equal to, okay, if I cube a negative number, I get a negative still. And plus and minus becomes minus. And what I notice here, this has a common factor of minus, or of -1. And what I really notice here is this is the opposite of the original function. So the original function was x cubed plus x, and therefore it's equal to opposite of f of x. And therefore, since this statement right here is true, it is odd. All right, so I hope you guys learned a lot. I will see you guys tomorrow. Have a good time.